An object is placed near a concave mirror, pretty close to it this time, as shown in this figure. So we're going to start by drawing a ray diagram to determine if it's real or virtual, upright or inverted, and larger or smaller than the object. So, drawing a few of the rays, the first one from the top of the object is the P ray. That's the one that starts out parallel to the axis. So, just does that small little bit right there. When it hits the mirror, it reflects off and passes through the focal point. So reflect it backward through the focal point and just keep it going. So that's the first one. The next one is the F ray. If I go from the top of the object toward F, that's going away from the mirror. So to draw the F ray, it says to draw on a line containing the F. So instead of going toward the F, put your ruler on it, but draw the line from the top of the object going directly away from the F. So that one will look kind of like this, going away from it. When it hits the mirror, it reflects and goes parallel to the axis. So you can draw this one going like that. Notice right now that the reflected rays, this one and this one, diverge away from each other. So there's no point where they're going to cross, so that implies that we're going to have to trace the reflected parts backward to find out where the final image is formed. But let's just do one more ray, and I'll go ahead and draw the M ray for this one, which is from the top of the object to the midpoint of the mirror, and that one just reflects at the same angle to the normal. So this angle and this angle are the same. So let's take each of these three rays, since they're all diverging away from each other, and trace them backward to the other side of the mirror using a dotted line. So I'll start with the P ray, which was the purple one. It reflected, when it reflected, it went down through the focal point. So if I trace that reflected part up like this, we have that. Then I'll go to the red one, which was the F ray. The reflected part was parallel, so I'm going to trace that reflected part backward. And finally the midpoint ray, that's the one that the reflected part, if I trace that backward, is going to be like this. And you can see that all three of those rays crossed at the same point on that side of the mirror. So I can draw the final image from the axis to that point. And I'll use black for that final image. So draw an upright arrow right there. So based on that image, we can tell that since it's on the other side of the mirror from where the object is, that means it is virtual. Since the arrow is pointing upward, we can say that the image is upright as opposed to inverted. And we can tell just by looking at the size of the arrow, this one is bigger than this arrow, so the final image is larger than the object. So let's verify it with the math. So in part B, determine the image distance. So take the mirror equation, rearrange for 1 over di, which is 1 over f minus 1 over do. So that's going to be 1 over, it says the mirror has a focal length of 20 centimeters. I'll go ahead and put this information down. The focal length was given as 20 centimeters. The object has a height of 2 centimeters, and the object is placed 10 centimeters from the mirror, which is half of the focal length. So, and it looks like that in the diagram, that the object is halfway between the focal length and the mirror. So plugging these numbers in, we have 1 over 20 minus 1 over 10. The common denominator is 20, so it'll just be 1 over 20 minus 2 over 20, which is negative 1 over 20. So the di is equal to the reciprocal of that. The reciprocal of negative 1 over 20 is negative 20 centimeters. Notice that because this is a negative number, anytime the di is negative, that means that the image is virtual. So that checks out with what we had up here. For part C, the magnification is equal to negative di over do. The di is negative 20, so we have a negative 20 divided by the do of 10. The two negatives cancel out to leave you with a positive 2 for the magnification. The positive sign means that the image is upright, so that checks out. And the numerical part, because it's greater than 1, means that the image is larger, so that too checks out. And then for part D, the image height, when you rearrange the other form of the magnification equation, the image height is equal to the magnification times the height of the object, which is the positive 2, times the height of the object, which is also 2, and you get an answer of 4 centimeters.